All right, time for the take-home magnetism inductance test, the free response part. 2 free response problems in 30 minutes. Here we go. This first one, we've got this square loop of wire, side length S, resistance R, getting pulled at a constant speed, pulling it out of a uniform magnetic field that's got a intensity or a strength of capital B. You see all the dots telling me the field's going out of the page. The plane of the loop is always perpendicular to the magnetic field. So plane of the loop, right, in the plane of the loop, magnetic field, we're at right angles to each other. After the leading edge of the loop has passed the edge of the B field as shown, there's an induced current. Sure, as it starts coming out, I'm getting less and less flux through that loop, and so I'll get a changing flux makes a voltage in that loop of wire that's going to push current around. So they say on the figure above indicate the direction of the induced current. And so you say, well, that induced current, you say if this is my loop of wire, right, and what's happening here is I got my magnetic field, that's dots. You say, I'm getting, as this goes through, I'm getting less and less field lines shooting up out through the loop. So the induced current has to flow so that its field fights the change. Getting less flux up, so current has to flow to make more flux go up. So I'm going to use my third right-hand rule, the one that's especially for loops of wire. That's the one where my fingers curl with the current and thumb points the direction of the flux through the middle of the loop. So I'm trying to make more flux go up because as this goes out, we're getting less and less up. So current has to flow to make more go up. The current's going to have to go counterclockwise. So my induced current, I should have an arrow showing that my induced current is going to go counterclockwise. I induced. Okay, and that's part A. Okay, counterclockwise. Okay, part B says using Faraday's law of induction, develop an expression for the induced EMF in the loop. So that voltage I'm going to go around the loop. You say, well, Faraday's law, you should say right away, okay, that's the EMF is negative d phi b dt. Yeah. And you say, how do I calculate flux? It's going to be a negative d dt of flux. Well, flux is the B dot dA, yeah? Okay, B field strength, that means field lines per area. So field lines per area times area is field lines, and that's what flux is. Now the B is, as I go over my area of my loop, you say, what's the area that I have that's changing? So the area of the loop, it's a square of side length S, but the part that's in the field is the part that we're interested in here, right? To get the flux, there's only flux in this part, right? In this part of the loop. Okay, well, they showed me that this was X. They called this length. So it's a square. I know I didn't draw a square very well. Sorry about that. Where this side length is S. So this is S times S minus X is the area, right? And notice that this integral is just the B times the area that we have. That's this area. I'm going to worry about the derivative with respect to time later. This is just adding up B field over that area. Well, the B is uniform everywhere in that area, so it would pop out. An area vector is what we're dotting with here. Area vectors go straight out of the plane of that area, of that loop. So my area vector is sticking straight up along the B field line. I'm going to call that a cosine of 0 degrees everywhere in that loop, in that area. So B is a constant, cosine theta is 0 is a constant. And so it's just integral dA, that's just the area. That's just the total area. So that's just B times A. So I got that integral just becomes B times A. You see, well, the A, like I said, I could calculate the area as being length times width. So that's going to be S times, and then the width is not the full. I just want the area that's got flux through it. So that's S minus the X is this bit. So that's my area. Now I want to get the EMF, I want the rate of change of this, right? And as this goes through, you know, let me go ahead and I'm going to FOIL this out. I'm going to go ahead and distribute out that BS. Yeah, I'm going to distribute out the BS. That sounds oh, sorry. Well, yeah, sure. Distribute out the ds. So it'd be bs squared minus bsx, right? And you say, well, this is a constant. These aren't changing as the thing moves. With time, though, but that x is changing, right? The length of x changes. So this term drops out. When I take the derivative, it's going to be 0. It's going to be negative derivative with respect to time of, derivative of the sum is sum of the derivatives, just this term, of negative bsx. And you say the derivative of bsx, that's just going to be negative bs, negative bs dx dt, right, is what I'm going to get. And you should say, hey, dx dt, that's just v. We were told the velocity of this thing going to the right is v. So that's actually just, and the negative cancel. It's just going to be, my induced EMF is going to be BSV. There we go. That was a lot of work to get to that. Sorry about that. But yeah, yep, that's the way it works. Yeah, I'm good with that. Okay, next part of the free response. Part C, they want you to determine the induced current in the loop. Okay, and so you say, okay, well, the induced current, I know that my induced current, okay, well, this is the induced EMF, is what I just got here, right? And I say, well, they told you it was a loop of resistance R, so I just say delta V is IR, right? I know the resistance, I know the voltage is this EMF, and so I'm just going to say, oh, well, that current is going to be delta V over R, and so that's that induced EMF divided by the resistance. That's it. And part D, they want to know the power required to keep the loop moving at constant velocity. And so for that, you're supposed to say, okay, power is that change in energy per time, how quickly we're changing energy, right? Pumping energy in. And so you say, well, I can think about this, that energy that I'm pumping in, that's going towards pushing the charges around in that loop. And that energy that I'm giving the charges, where is it going? Well, that resistor is burning it off as heat. That resistance is burning off, turning into heat. We have a formula for that. That's current times voltage. That's the rate at which a resistor converts energy to heat, or we're taking energy out of a battery or whatever. It's current times voltage, right? So that's it. I'm just going to do the current times the voltage. The current we just calculated there, and the voltage, that's that induced EMF we calculated there. So I just want to take the current times the voltage, right? So that power is going to be BSV over R times BSV, and that's just going to be B squared S squared V squared over R. That is my power. That's how fast we're burning off energy. Well, that's how fast we're putting energy in. If thing's going to go at constant speed, not gain or lose energy, then that's the deal. Hey, that's it. I could calculate that another way if I wanted to. The reason why I have to keep pulling on this to keep it moving and keep that current flowing, but to keep it going constant speed. If I didn't keep pulling on it, it would slow to a stop. The energy has to be, the energy that's going towards being burned up, the current, right? So it's going to take away from the only place it has energy, and that's the kinetic energy of it moving. So I'd have to keep pulling to keep giving it the energy. Well, how exactly does it slow the thing down? Well, this induced current would be flowing across, in this part here, would flow across field lines, and so it would get shoved. You say, what about the current here? Well, the current here, V cross B, the force would be up. That doesn't fight against the sideways motion. And more importantly, current going to the right, V cross B would push down. So I had a force up and down here that would cancel. But this part isn't going to be canceled. That current flowing through here is crossing these magnetic field lines out. So if I do V cross B, there'd be a force to the left, a magnetic force to the left on that wire. And so I would have to tug to balance this external force from me. I'd have to balance that out to keep it moving constant speed. So I could do my power rating, how quickly I'm pumping energy in to keep the thing moving, right? I'd have to balance out this force and say, well, power, the energy I pump in, that's like work per time, right? You know what I mean? how quickly I'm doing that. And you say, well, work, that's like force through a distance, right? Through time. I know I'm doing the non-derivative way. Well, fine, if you want to do it like this. Fine, this would be dx over dt. And dx over dt, that's just f dot v. Okay, and that is on the formula sheet, I think. Power is f dot v. I really should have a formula sheet handy when I do these. But anyway, it's f times v. And so you say, well, gosh, the force then, I'm just balancing out that magnetic force. What's the magnetic force? It's IL cross B. That's the force on a current carrying wire. And you say, well, the I, we figured out, was BSV over R. BSV over the resistance. And the length of the wire, well, that's just that S times the B times the V. And so you say, oh, well, that's just going to be B squared S squared V squared over R. And that's the same thing we got there the other way. So yeah, yep. Okay, hey, that was that for response problem. Let's go to the second one. So the second free response problem looked like this. I've got a rectangular loop here of wire that's located next to a long straight wire that's carrying a current. And they give you an equation for the current that my current is my max current times sine of omega t, I max sine of omega t. So that current's going to be changing with time. We already can kind of anticipate what this problem is going to be about. Current goes along, field going out. I'm going to have field going through this loop, but because the current's changing, the field strength will change, and that will be a changing flux through the loop, which will induce a voltage and make current flow around in the loop. You're like already looking forward to this problem. Here we go. They went out, the loop and the plane are fixed in space. So I don't have to worry about like forces tugging things around. They're locked in place. Okay, using Ampere's law, show the magnetic field intensity at a distance r from the wire is mu naught I over 2 pi r, with mu naught being the permeability of free space. We're just proving that equation for a long straight wire. You say, oh, okay, that's fine. That's fine. I can do that. That's Ampere's law. So I got my wire. I'm trying to find the magnetic field strength at some position out here somewhere, you know, say right there. Hey, what's the B field strength where that is some distance r, right? I've got my current flowing in that wire. And so you say, well, Ampere's law says we're going to go ahead and integral over a closed path, B dot dl, is mu naught times the current going in through the path. That's Ampere's law. So for this one, I have to choose a path. I'd like to choose a path that makes this integral easy to take. I'm going to be looking at like each little bit of my path length dotted with the B field there. It'd be great if the angle between B and DL was constant, right? So you say, oh, wait, what's the field going to look like? Use my second right-hand rule. Grab the wire, thumb the direction of the current with fingers curl. That's where the field loops around the wire. So my field's coming out of the page up here. I'd have dots for my field here. My field will get weaker as I go farther away. I'm trying to find the field strength. I have X's on this side. Yeah, we got it. Anyway, point is I'm trying to find the field strength there. So I want to make my path go through there. If I did an end-on view of the wire, I'd be trying to find the field strength at some point, right, out here, right, at a distance r away. Well, the field lines loop around the wire. So I'm looking at it from this side. I don't know. Let's say my current would be like an X, right? It would be the current going in that way, right? If I'm looking from the left end here. And the field lines, grab the wire, thumb the direction. Current field lines would loop around like this. So a magnetic field would be looping around the wire like this, right? Okay, and that's what I'm seeing as dots here and X's down there, right? Okay, we get it, right? Okay. So I'm going to choose my path. By symmetry, it should be the same strength everywhere out there along a circle. So my path, I'm going to choose a path that goes along like this. I'm going to add up my B dot, my DL, the length of path. Each of these little DLs going around, B dot DL. It's going to be nice and parallel. So this is going to give me a cosine of 0 degrees everywhere on that path. And because it's uniform, same distance away all the way around. It's going to be the same field strength all the way, so that b will be a constant. So the b will pop out. Cosine of 0 degrees pops out, factors out of the integral. So it's just the integral over the loop of dl. We'll just add up the length all the way around. That's just 2 pi r. So this is just going to be b times 2 pi r mu naught. What's the current that goes in? Well, it's just the current in the wire, which they called I, right? And so my b is mu naught I over 2 pi r. Ta-da! Which is what we're supposed to show. Okay, part B. They say, find the magnetic flux through the loop at time t. Okay, so you say, okay, finding flux. I'm like, okay, flux is just integral of b dot dA, right? I'm not doing for a closed surface. It's not Gauss's law. I'm just looking at the flux through that area. The area I'm talking about is the area of this loop. I just want the flux going through that loop. Let me draw that picture. Let me draw that picture down here. I should have drawn that. Okay, we've got a length here of L, and this has got a width there of B, and it's a distance A away. Okay, I want the flux that's shooting through this for that field made by this current I flowing there. So I would just say, hey, this integral is just b dot dA, right? And you say, the problem is the B field is not going to be the same strength everywhere in this area. As I go farther away from the wire, the B field gets weaker, right? According to this equation. So I'm really doing my integral. I'm going to substitute that in there for B, right? So my flux is going to be the integral of mu naught I over 2 pi r. Okay. dA. Right. Now as far as the dot goes, field's going out. My area vector I make go out. This is just gonna be like a cosine of 0. Okay. Right. I'm gonna assume it's I'm gonna make that a cosine 0. Okay. You can make it 180 if you really want to, but all right. Anyway, so when I look at this, then you're saying, okay, my dA. Now, how am I going to do this? The B field strength is changing as I go up away from the wire. The B field strength changes. So I want to split this up into a bunch of little D areas. I'd love for this field strength to be the same everywhere in each little dA. In other words, I want to keep that R value the same, constant throughout one of these slices that I slice it. So I'm not going to slice it up this way, slice that area to get little dAs. I'm going to slice it this way, slice. So each slice is at a constant radius out, so I have a constant B field strength along that slice. That's the idea. So what does a little dA look like? Like I said, I'm going to slice it up. Right? One little slice will have an area dA. And you say, hey, what's that dA going to be? It's going to be an infinitesimal thin little thickness this way, dr, right? And it'll have a length of L. So LdR is dA. So to find my flux, I'm going to integrate mu naught I over 2 pi 1 over r, and then that's cosine 0, L dr. Okay, what are my bounds anyway? I want to find all the flux through this loop. So it's going to be from r equals a to r equals a plus b. I like to do 2 integral signs to remind myself it's an area that I'm dealing with here. I don't mean it to be like a double integral. I'm just trying to remind myself it's 2 dimensions, but now I'm doing it in terms of r, so I'm just putting 1 integral. I know, you don't really care about my notation. Anyway, that's what I'm doing. Hey, when I do this integral with respect to r, mu naught, I, 2 pi, and L, they're all constants as a function of r. So that'll kicks out. So it's just going to be the integral. So mu naught I over 2 pi L. So it's the integral of 1 over r dr. Okay, from a to a plus b. And everyone recognizes that 1 over r integral as being that weird, freaky special case. That's like the natural log of the absolute value of r, evaluated from a to a plus b. And you say, hey, that would be the natural log of a plus b minus the natural log of a. And you say, I can make that a nice cool division thingy here with that, properties of logarithms like that. Okay, these are all constant values, so I don't need the absolute value sign, because a and b and a, those are all just constant values. Okay, so when I do that then, hey, this was in front, that's still hanging out. So mu naught I L over 2 pi times natural log a plus b over a. That is my flux. That's my answer. All right. Great. Okay, so what comes next? Moving on to part C. By the way, how they told you that the current was I max sine of omega t? So I could put I max sine omega t in there where it says I if I wanted to, but they're giving me I as a variable, so I can just leave it in terms of I. I don't need to put but if I did that, if you did put that I max sine omega t in there, that's just fine. That's just fine. You can do that. Okay, let's go to part C. Part C, now they say the current now is in the direction shown above, that would be to the right, from time 0 to time pi over omega. And you say, okay, wait, what's special about pi over omega? Well, the sine of omega times pi over omega, omega would cancel, it would be the sine of pi, and the sine of pi that's when the function goes from 0 around to pi, that's when sine goes back to 0, it's about to go negative. Right, so that's what it's about to switch directions. So yeah, that makes sense. Okay, indicate the diagram in the direction they reduce the resulting current that's induced in the loop at that time. Okay, so I got too many pictures here. The direction of the induced current. Okay. The current is going to the right, and the current is dying down, right? When it gets proportional to sine of omega t. And so when that sine omega t at t equals pi over omega, that's when it becomes sine of 0. I mean sine of 180. And sine function, from unit circle, right? Sine is like the vertical part. When this angle gets all the way over to here, that's when the vertical part, when the sine goes to 0 here at pi, right? And so the point is, when I get to there, that's when I'm going from having field. My field is 0 at that point. Actually, the magnetic current, the current is 0 at that point, so the field would be at 0. So the field would have been decreasing in strength to that point. Up to that point, my current's going this, and I have flux coming out of the page. My flux would be decreasing to be at 0 at that point, and then continue going more and more negative. So they want to know. The direction of the resulting current that I'm inducing. I am decreasing flux out of the page. That's what's happening all through that time. All the way from when I've got that sine of pi over 2 to when I have that sine down here, my flux is going to be decreasing, right? And so my flux is decreasing, less and less flux out of the page. So current has to flow to make more flux come out of the page. Using the third right-hand rule for loops, the induced current's got to go so that I make more flux out. It means the induced current's got to go this way. Fingers with the current, thumb is the field through the middle of the loop. So it's going to do this and make more flux out. It's got to be counterclockwise. So my answer for CI, I've got to indicate that the induced current is going to go counterclockwise around that loop. I induced. Okay, and then that was CI. And now CII, determine the EMF that we induce at that time, when time is pi over omega. Okay, so I want the induced EMF. And so you would say, well, So C I was counterclockwise. So now C part I, right? You say, I want the induced EMF, and that's negative d phi b dt, right? Faraday's law of electromagnetic induction. You say, how am I going to calculate the flux? That'll be the integral of b dot dA. You say, what am I doing? We calculated the flux here. Now I just want the rate of change of flux. Sorry, the rate of change of this function that we got before. So, sorry, what a mess. Sorry about that. My induced EMF, negative d dt of mu naught I L over 2 pi natural log A plus B over A. And you say, but wait, which of these are changing with time? Mu naught doesn't change. The length of this loop doesn't change. 2 pi, natural log of this, those are all constants. It's just the I that's changing. All that constants, I could just kick all those out right now if that's going to make me feel better. It does. It does make me feel kind of better to get all those constants out of the way. So I'm just looking at what? The ddt of the current. You say, now what's the equation for current? That's the one they gave us. They said the current was I max sine of omega t, right? So I'm going to do the ddt of that. Well, the ddt of that, I max is a constant. That coefficient will kick out. So I'm just taking the derivative of sine. Derivative of sine is cosine, right? Yeah, cosine of omega t. But there was a function inside the sine function. There's an omega t, and the derivative, so I got to multiply the derivative. That's that chain rule idea. The derivative of omega t is omega, so that's going to kick an omega out. So I'll have I max omega cosine of omega t. So yeah, so that's what this derivative is turning into. I still have all this junk in front. Now they said specifically they wanted the induced voltage at time pi over omega. So I can just go ahead where it says t and stick in pi over omega. That'll make it a cosine of omega times pi over omega. It's just a cosine of pi, and the cosine of pi is -1. So this is just going to be I max omega times -1, right? Okay, and I still have this bit in front coming down. This negative and that negative are going to cancel each other. So I'm going to get mu naught L over 2 pi. The order I put these in is not so important. A plus B over A, and I have this I max omega. All right, and that is going to be my answer for the induced EMF at that time. Okay, and that's the free response.